Okay. How's everybody? We have 25 people. Can you guys hear me?
Yeah, we can hear you.
Sounds good. Okay. Any question before we begin? And sorry for the big delay on, posting the exam 2 homework. I received probably over 20 emails. I know people are nervous, frustrated, but it was finally done, along with the quiz 9. Also, any chance we could go over 10-point number 11? Sure. Who's asking that? Chase. Which Chase is that? Chase Falco? Or is this Chase Howie? Alright, how's Bill? Number 11. Yeah, we can do that one. Actually, before doing that one, let me, we already know how to find, for example, gamma of 5, right? Gamma function was what? So what is gamma of 5? How many factorials? It's 4 factorials, right? Which is 24 in this case. So as long as the argument of gamma is an integer, so if it's, n plus 1, then it's n factorial. Is that correct? Now, what if the argument is not integer? So I have a specific case, and that's, what is gamma, for example, of half? Like, we don't have, negative 1/2 factorial. Like, if you wanted to use this formula, that's how you would write it, right? But this doesn't make sense. Okay, so let's see if I can prove it on the rest of this page. But before that, I'm going to take you back to a specific integration. Let's I'm going to remind you guys this integration, e to the negative x squared dx, 0 to infinity, okay? In fact, e to the negative x squared at 0 is 1, and then at infinity is 0, so it goes like this. And that integral is simply the area of the region underneath the graph above x-axis from 0 to infinity. And that's a finite number, like that area. Of course, it's a finite value. Area. Does anybody know what that number is? I don't expect you to know it. But most likely you did it in Calc 3. Okay. I'm going to remind you how to do it. I'm going to call this guy, I'm going to call that value capital A. Okay? But instead of A, let me find A square, and then at the end I square root it, right? And then that gives me the value of integration. So that area, if it's A, at the moment I'm finding A square. All right. So what is A square? It's simply A times A, which is integral from 0 to infinity negative x squared dx. I'm going to multiply by itself, but this time I want to change the variable. So this time let me use variable y, e to the negative y squared dy. Right? These two have the same exact value. I'm just changing the variable from x to y. It has the same value in integration. Now I can go ahead and write this. In fact, one of each integral is constant with respect to the other variable. So I can write it this way. I can write it 0 to infinity, 0 to infinity, e to the negative x square, right? dx. Just imagine you are, pushing this inside this integral as a constant. So it's going to be like that, right? And then I can go ahead and write it as 0 to infinity, double integral, 0 to infinity, e to the negative x square, negative y square, dx, dy. Question so far? Let me rewrite it one more time. And it goes like that. Only factor the negative in the exponent of e. Now, I have a question. Do you remember how you guys did such integral? It's a definite integral, double, right? It's a double integral, definite. You have limits for x and y. And you have a function e raised to the negative. Let me pause. X squared plus y squared. X squared plus y squared, dx, dy. You did a change of variable. Do you remember what system you used? What kind of coordinates? Nice. You convert it to polar coordinate. And polar coordinate, we had that equation between x and y, and radius, which was the distance from the origin, and theta was basically from 0 to pi. But in this case, what's the region? X is going from 0 to infinity, and y is also going from 0 to infinity. So we only on this region. On this region, your theta is going from 0 to pi over 2, and it's the entire thing. So r is going from 0 to infinity. And we had a Jacobian, right, term involved. So it's 0 to, let's do 0 pi over 2. So 0 to pi over 2 for theta, d theta. 0 to infinity, e to the negative r square. I'm replacing this with r square. And what was the Jacobian term? It was r dr. Now this integral is doable. Remember, the reason we did this whole thing because e to the negative x square has no antiderivative. There's no function that can be found for which you take derivative and derivative equals that guy. There's no such function. There's no algebraic function doing that, right? You can, come up with Taylor series maybe, or Maclaurin series, but not a one single term analytical function. So let me erase this. So that's the reason we're doing this, okay? So there's no theta in this piece, right? So theta is just going to be integration from 0 to pi over 2. D theta is pi over 2. And what is your integrand? Your integrand is r e to the negative r square. You do a substitution, and integration is negative half e to the negative r square. So that's the integration of r e to the negative r square. Let's evaluate it from 0 to infinity. And now this is pi over 2 times. If you plug infinity, you get 0. Oops. 0. And if you plug 0, you get plus half. So that your a square is pi over 2. Pi over 4, sorry. So a, simply take square root, it's going to be root pi over 2. That means the integral from 0 to infinity e to the negative x square dx is root pi over 2. All right. You might say, why do we care about this in Laplace? Be patient. Now, I would like to find gamma of half. Okay. Now for this, we're going to go ahead and use a formula, right? What was gamma function? It was 0 to infinity. Let me write down the gamma definition first, and let me use that. So gamma of x in general was 0 to infinity, right? E to the negative t, t to the x minus 1, the dt. That was the definition of gamma of x. Now let's write down the formula for gamma of half. So 0 to infinity, e to the negative t raised to half minus 1 dt. Let's simplify. 0 to infinity, e to the negative t raised to the negative half dt. This integration, like we don't want to waste our time doing by parts. Let's do one simple substitution. Okay, and this is my substitution. I'm gonna let's go ahead and let t be x squared, and you'll see the reason. First of all, dt is 2x dx. Good. And from here, if you raise both sides to the negative half, you'll see it's going to be x to the negative 1, right? Which is 1 over x. Good. All right, now let's substitute. And by the way, when t goes from 0 to infinity, x also goes from 0 to infinity. So it becomes 0 to infinity. Now, remember, I want to change the variable of integration from t to x. So it's e to the negative x squared, or replace t with x squared. T to the negative half is 1 over x, and dt is 2x dx. Let's simplify. It's 0 to infinity. 2 is a constant. Let's pull it out. The x and x cancel, so we get e to the negative x squared dx. Now we can see why we found this guy. Right? We already found the value of that integration. So it's 2 times root pi over 2. 2 and 2 cancel. There you go. You have the gamma of half. Thus, gamma of half is square root of pi. Okay. Now, Chase. Number 11. It's asking to find the Laplace of root t plus 3t. Is the room up? No. So we said Laplace has the linear property, right? You can do each term at a time and then pull out any constants. So this is Laplace of t to the half plus 3 is a constant, Laplace of t. Okay. Now remember, Laplace of t to the n in general was t to the a. Let's write it this way. T to the a was gamma of a plus 1 over s to the a plus 1. So using that formula, this is going to be, so gamma of t to the half, like a is half, so it's going to be gamma of 3 over 2 over s to the 3 over 2, right? Remember, you add plus 3 times gamma of 2 because the power of t here is 1 over s squared. Okay? So that's the denominator of that guy. We know what gamma is when it's integer, so it's 3 times 1 factorial over s squared. Now, what is gamma of 3 over 2? Well, if you remember, gamma of n in general was n times, let me do n plus 1. So gamma of n plus 1 was n times gamma of n. So that gamma of 3 over 2 is half times gamma of half. Oops. So you're going to have half times root pi s over s raised to the 3 halves plus 3 over s squared. That's it. That's the Laplace transform of the above function. Good. My handwriting is worse when I do it on the tablet, the iPad. I'm not used to it. Anything else? And don't worry, that was part of the lesson today, so I'm glad you asked that question. Thank you. All right. So, let me mention that by the whole fact that gamma of 1 over 2 is root pi, you can find, for example, gamma of 5 over 2. Well, recursively go ahead and use this formula. So this is, 3 over 2 gamma of 3 over 2. Then it's 3 over 2 times half gamma of half. Like, you repeat this until you get to the piece we already know what is gamma for, okay? So that's 3/4 and then root pi. That's it. Like, that's gamma of 5 over 2. You can do the same thing, maybe 4 times to find gamma, for example, of 9 over 2. Same process, okay? All right. Any question on that? Okay. So we are still building, this foundation of Laplace of multiple functions, different functions, so that we can look at the inverse and then apply it into solving differential equations. I don't know if you have the textbook in front of you. This table is something that you can use during quiz. So I'm not going to give you the formula. Table 10.1, 10.1.2. Okay, it's on page 562, section 10.1. So use table 10.2.1, 10.1.2. It's the, Laplace transforms. So using that table only is okay. It's not considered cheating. I'm allowing you to do that. My voice is being recorded, so you have that proof. Only that table, though. Okay. And if you look at the table, if you have the book in front of you, we have already talked about 1, 2, 3, 4. The first 5 rows of that table. Like, we talked about Laplace of 1, Laplace of t, t to the n, t to the a, and then e to the at, right? We have already found Laplaces of those guys. Now I'm going to continue finding Laplace of the next 4. I'm going to skip the last one, until we encounter a problem that maybe we're going to deal with that, mostly with the inverse of that. And I'll come back to it. It's basically a piecewise function. I mentioned it when you guys did it in problems 1 through 4 or 5. But the last 4, like trig functions, are the ones that I'm going to talk about. Okay? All right. Let me start with, first of all, I assume everybody knows between this function and that function, right? The one that has h in it. What does it stand for? Sine hyperbolic. Do you know why we call it hyperbolic? Doesn't even know why it's called hyperbolic? Here's the reason. Everybody knows that identity for sine and cosine, right? So if you replace sine with x and cosine with y, you get this equation. What's the shape, or what picture does that equation generate? Nice. Circle. Now, first of all, sine hyperbolic of x and cosine hyperbolic of x, or t, have these equations. Sine hyperbolic is defined as e to the t minus e to the negative t divided by 2, and cosine hyperbolic of t is same thing except negative becomes plus. So e to the t plus e to the negative t divided by 2. Okay? It can be shown, it's very simple algebra. It can be shown that cosine hyperbolic square of t minus sine hyperbolic square of t equals 1. It's very simple. All you have to do, plug, you do e to the t plus e to the negative t divided by 2 squared minus e to the t minus e to the negative t divided by 2 squared. Foil, cancel, combine like terms, and you see it's 1. It's a very simple process. Now, if you let cosine be x, what equation are we going to get? And y, sine h of t, let it y, so this x and that y and this one x. The equation we're going to get, x squared minus y squared equals 1. Now, this is also a conic section. So this one is going to generate a circle. By the way, that's the cool thing I found out about this app. So that's going to generate a circle. Now, what shape is that one going to generate? Nice. It's going to generate this guy called hyperbola. That's the reason they're calling these functions hyperbolic functions. Okay, so that was a little bit of a story behind it, why it's called hyperbolic. Anyway, now we are interested to find Laplace of sine hyperbolic of t and then Laplace of cosine hyperbolic of t. It's a very simple in this case, think about it. Sine h, according to the definition, a Laplace of half, right? E to the t minus e to the negative t. Correct? Half is a constant, so it's half. All right. Laplace of e to the t. Okay? Let me write that down. So Laplace of e to the t, Laplace of e to the negative t. Okay? Let me erase this for now. Equals half. All right. Now you can have that table in front of you. Oh, that's a nice hyperbola. You have Eli. So what is Laplace of e to the t, guys? You can look at the table, the one on page, whatever it was, 562. So Laplace of e to the t, in fact, is the 5th row of that table. Laplace of e to the t. Thank you, Will. I know, it takes time to type it, but I appreciate doing that. It's 1 over s minus 1. Similarly, I made a mistake here. So this should be minus, guys. Let me zoom in so, I can only erase that one. Damn it, I erased the whole thing. But, I can still write. So it's Laplace of e to the t minus Laplace of e to the negative t. So it's minus, and similarly, that one is s plus 1. Oh, we have two fractions, we add them, right? So I'm not gonna go over the details, skip that algebra. You'll see it's gonna be half times 2 over s squared minus 1, because if you multiply s minus 1 and s plus 1, you get s squared minus 1, right? 2 and 2 cancels, so that you have 1 over s squared minus 1. So this is the Laplace of sine hyperbolic of t. Right? Maybe I should have done it in general for k, so you could have seen, but it's okay. I'll do the cosine hyperbolic for k, and you get the idea. All right, now this time I'm going to do the Laplace of cosine hyperbolic. Instead of t in general, let's say it's kt. Okay. All right, let's write down definition. It's e to the kt plus e to the negative kt divided by 2. Same thing, half is a constant. Okay. So it's Laplace of e to the kt plus Laplace of e to the negative kt. So it's half. All right. According to the table, we have already proved this. It's s minus k plus 1 over s plus k, or e to the negative k. Oh, h, it's the first letter of hyperbolic. So sine hyperbolic of t. cosine hyperbolic of t. You're welcome. So it's half, again, algebra, and if you do it, you see it's going to be 2s over s squared minus k squared. 2 cancels, so you have s over s squared minus k squared. Oh, come on. S over s squared minus k squared. Okay. I mean, up there we proved it for, basically we did sine hyperbolic when k is 1, but it's a very simple process to figure, sine hyperbolic of kt will be k over s squared minus k squared. Okay. And these two are exactly the, from the bottom, 2 rows from the bottom. I mean, the second and third row from the bottom in that table, sine h of kt and cosine hyperbolic of kt. All right. Now, question so far? I'm going to continue with just a normal trig function, sine and cosine. All right. So let me start with this guy, e to the it. Do you remember the Euler formula? This was equal to cosine of t plus I sine of t. Now I'm going to go ahead and change the sign of the exponent and write e to the negative it. Well, this is basically simply, e to the I times negative t. So replace the argument here with negative t. It becomes cosine of negative t plus I sine of negative t. Negative t. Cosine is even function, so cosine of negative t is just cosine of t, but sine is odd, so it becomes negative of that. So it's negative I sine of t. All right, guys, I have a question for you. I'm going to go ahead and add these two guys. So what is e to the it plus e to the negative it? Well, simply I'm adding the right side with that guy. Now, 2 terms cancel out. Do you see it? When you add those two, the negative I sine t and I sine t way. So what are we left with? I'm not multiplying, Alex. I'm adding them simply. So add these two terms together. Yep, you're going to be left with 2 cosine t. 2 cosine t. So that if you solve for cosine t is, e to the it plus e to the negative it divided by 2. Some of you might have seen this before. And if you subtract them, you'll see simply it's 2i sine t, right? Because you're changing the signs here, and here, you're changing the signs to negative and positive. This time cosine cancels out, and you get 2 times I sine t. Okay? Now, to get sine by itself, you divide by 2i this time, so be careful about that. It's e to the it minus e to the negative it divided by 2i. All right, now we're going to use this to find Laplace of sine and cosine. Let's start with Laplace of cosine. So, Laplace of cosine of t equals, again, it's linear, so we can pull out the half. That means it's going to be Laplace of e to the it plus Laplace of e to the negative it. We're going to, again, use the formula for the Laplace of exponential e to the at, except here a is the imaginary number I, okay? So it's going to be half. So it's 1 over s minus I plus 1 over s plus I. That's the difference. Okay? Now, same thing. Add these two fractions, you're going to get a common denominator. Except the common denominator, I'll do the algebra here for this one. All right, so it's going to be s squared minus is plus is minus I squared. What is I squared? minus 1. Minus minus 1 is plus 1. So these two cancel. That means this is nothing but s squared plus 1. Okay? And if you add them, you're going to get, let's start with this. So it's going to be half times 2s over s squared plus 1. 2 and 2 cancels, so that you're left with s over s squared plus 1. Okay? I'll leave this here for people who want to, figure out what happened over there. Now, let me find the Laplace of, instead of sine t, let me change the argument to kt. And we can make an analogy between the table in front of us and this proof right here. Okay, so it's going to be, let me write this one down. So it's going to be Laplace of half e to the I. Kt, remember, I'm changing the argument from t to kt in this formula right here. Let me circle that one right there. Okay, and then minus e to the negative I times kt. Okay, so we use the linearity of Laplace, so it's going to be half Laplace of e to the, let me write it this way now, ikt minus e raised to the negative ik times t. You know what, let me close this bracket here, minus Laplace of this. How about that? Okay, half. All right, same setup. So this one is going to be 1 over s minus ik minus 1 over s plus ik. Okay. Again, common denominator, right? Subtract those two fractions. You'll see that this is, guys, I'm missing something. Can someone tell me what I'm missing? What's the denominator of that ratio? 2i. I'm missing that I. So this should be 1 over 2i. I. Okay. So it's going to be 1 over 2i. So very simple. If you multiply those two, you see it's going to be s squared plus k squared. And subtracting them, it's going to be 2ik. That's why you need that I to be able to cancel out, okay? So that eventually Laplace of sine of kt is k over s squared plus k squared. And Laplace of cosine kt, we already showed that for k equal 1, but we can do the same process. It will be s over s squared plus k squared. Okay? Basically, for sine, the numerator is constant, k. For cosine is s, is the variable s, okay? But denominators for both of them is the same, s squared plus k squared. And same scenario for sine hyperbolic and cosine hyperbolic, in fact. But instead, denominator is s squared minus k squared. That's the difference. Okay. We did it. Now, let's do, a couple examples. Let's start with this. What is Laplace of 3 sine of 2t minus 7 cosine hyperbolic of 5t? Okay, let me write down that this is an example. So it's linear. Laplace is linear, so you can first of all write this as 3 times Laplace of sine of 2t minus 7, that's a constant, Laplace of cosine h of 5t. You already have the formulas, or you can get the formulas from the table you have in front of you. So the first one is 3 times. Okay, so that's sine, the normal sine. Okay, so and k is 2 here, right? K is 2, so it's going to be 2 over s squared plus 4. S squared plus 2 squared, which is 4, minus 7 times. Okay. So here, case 5. So denominator is S squared minus 5 squared, which is 25. And for cosine is always S on top. Right? And that's it. That's Laplace. One step, if you want to add them, maybe you want to multiply those numbers. So it's going to be 6 over S squared plus 4 minus 7S over S squared minus 25. So that's the Laplace of those two functions together, or that whole function. Question? 35. That wasn't bad. 35 minutes. I was able to talk about almost 1/4 of this stuff that I have planned to talk about. No questions? Okay. So far we talked about Laplace. Remember we had that machine? Oh, by the way, here's another cool thing. Rectangle. Boom. How cool is that? And I can change the size. So here's my Laplace transformation machine. From one side, you're sending, and let me use this again. Nice. So on one side, you're sending things inside functions of t, and on the other side, it's going to give you back f of s's. Okay, so this direction was the direction of Laplace, but this machine can work both ways, meaning not only you can give functions of t and given you Laplace transforms of s, right? You can also do the opposite. So if you give this machine a function of s, f of s, it's going to give you back the corresponding function in terms of t. So it works both ways. And of course, the other direction is simply Laplace inverse. So that's what it means, okay? Simple example. Laplace of 1. Do you guys remember what Laplace of 1 was? Is the first row of the table. Good. It's 1 over s. Right? Basically, inverse. The equivalent statement for this, for the inverse, is that Laplace inverse of 1 over s equals, what's that? 1. It's like inverse function, right? Like if a function, if g is a function and sends 1 to 3, that means g inverse sends 3 back to 1. That's all it does. Okay? So, and the two columns that you have on that table, basically you can go backward, right? Let's do, a couple more examples. We already know Laplace of e to the, for example, 3t is 1 over s minus 3, right? That means Laplace inverse of 1 over s minus 3 is e to the 3t, right? Now, if I ask you what's the Laplace of 1 over s minus 5, you say it's e raised to the 5t, right? What's the Laplace inverse of 1 over s plus 7? That's e raised to the, you tell me what the exponent is. You don't have to type e. So the exponent is negative 7t, right? And you can have the same thing for sine, we know Laplace of, for example, cosine of 2t is s over s squared plus 4, right? That means Laplace inverse of s over s squared plus 4 is cosine of 2t. Now I'm going to ask you this. What's the Laplace of s over s squared minus 9? What's that? You're missing one letter. Nope. Nope. There you go. That's the one. This negative, refers back to the hyperbolic, right? For normal cosine and sine, it was plus. For hyperbolic, it was negative. And since it's s, you have the cosine. And of course, the square root of 9, which is, 3 squared, tells you about the coefficient in front of t. Okay? So it's a very nice pattern, and you can identify the inverse functions of Laplaces. Okay? Let's do one example where we might need to do some partial fraction, and I'll explain what that means. Let's see. Or maybe you have to break it down, to two functions and then do the Laplace inverse. Here's a case. Let's do this one. So we would like to find the Laplace inverse. This is number 29. Yeah, it's number 29. 5 over s squared plus 9. I mean, the numerator is 5 minus 3s. So, okay. So we'd like to find the Laplace inverse of that. I mean, I should have mentioned something. Let me erase this. And as soon as I tell you this, you can easily figure this out. Similar to Laplace inverse has the linearity property. What does it mean? Simply, it means if you have, Laplace inverse of a times f of s plus maybe b capital G of s, then you can write this as a times Laplace inverse of f of s plus b times Laplace inverse of G of s. Okay. And then if the first one gives you function f of t, then it's a f of t plus b, maybe some g of t. Okay. Now you should be able to tell me what the original function of this Laplace transform is. What was it? 5 minus 3s over s squared plus 9. There you go. Okay. So what's the first thing you do? The first thing we do, very nice. So you split it up to fractions with the same denominator, right? So it's Laplace inverse of 5 over s squared plus 9 minus 3s over s squared plus 9. Okay. Then we use the linearity property. So it's the Laplace inverse, and you can pull out 5. So let's do that. 5 Laplace inverse of 1 over s squared plus 9 minus 3. Let me do something and tell me if it's wrong or correct. 3s and then 1 over Laplace inverse of s squared plus 9. Is this correct or not? What's wrong about it? Oh, definitely don't do that. Sure. What's wrong with it? Can you teach me what's wrong with it? The variable s. You're absolutely right. So you can now pull out the s. Okay. S is a variable here. Talking about this term right here. Let me use of course, I'm using the biggest eraser, the biggest dot. So let me use this one. So that was what? -3 Laplace inverse, and then here should be just s. Okay. Okay. Now we're good. Okay. Let's begin.
I think it should be +3.
I mean, we have a negative here. Are you referring to this guy?
Yeah. But no,
I'm counting for that
mind.
negative, right?
Yeah.
Right?
Yep.
Yeah. Is it okay now?
Yeah.
Okay. But thanks for mentioning that. It's always, nice to double check things. I make mistakes a lot. Okay, so it's going to be 5 times. All right. What function is that one telling you, giving you? Be careful. Close. Close. It's some scalar of that function. So you have, no, I already have 5t, so don't worry about it. I'm only asking about the Laplace inverse. Ignore 5. We have no 5 in there. Let me explain it this way. Let's start with the, damn, you got it. 1/3 sine 3t. There you go. You know what? Why is that? Remember, what I have here is only 1/3 of the Laplace of sine of 3t. Why is that? Because Laplace of sine 3t, right, according to the formula, was 3 over s squared plus 9, right? And I'm missing a 3 on top of that. So for that, this is what you can do, if it makes sense. I guess I have to go to the big one again. Oh, there you go. It's gone. So, what do I need here? So it was 1, right? So, well, put a 3 here, then put a 1/3 right there. That's it. Right? Remember, Laplace inverse of f of s is the same as 1 over k Laplace inverse of k f of s. These two are the same. So you can multiply and divide by any constant, just like integral, derivative, anything that you can play around with a scalar. Right? So for that reason, we can go ahead and write it as 5/3. Now we know it's sine 3t minus 3. That one is ready to perform the inverse. What is that one? There you go, cosine 3t. Right? So that's it. The Laplace inverse of that function in terms of s above is this guy. Or the other way, if you take Laplace of this function, you get the whole 5 minus 3s over s squared plus 9 back. Okay? Now, sometimes you might have to do partial fraction. We get to an example. There's nothing in this section 10.1, but we'll get those in 10.2. Okay, what time is it? 4:57. I suggest a break for, it's 4:58. Let's do a break until 4:55. How about that? For 7 minutes? Yeah, so we come back in 7 minutes, 4:55. So we come back at 4:55. And we start 10.2. Okay. Any questions? For example, we'll be given the table or using definition. I'll just ask you, you can use a definition and table in textbook, in the book. Okay. So let's continue on 10.2. Okay. So let me tell you what the goal is in 10.2. Basically, we want to start solving differential equations using Laplace transformations. Let me start with a simple example. Go to the first question on 10.2 where you have to solve differential equation. Let's go ahead and solve number 2. So number 2 is, it says solve this differential equation using Laplace transformation. But let's solve it with what we already know, okay, from chapter 5. We get the solution, and then we solve the Laplace transformation and see, how useful Laplace transformation is. And these are very simple equations. It solves even crazier differential equations. It's a very powerful tool. So let's solve x double prime plus 9x equals 0. And there are initial conditions given. X of 0 equals 3 and x prime of 0 equals 4. So let's use this using, what is it called? Characteristic equation or polynomial, right? What was it? Remember here, solution is x of t. Okay. So characteristic equation in this case was r squared plus 9 equals 0. Then, r is plus or minus 3i. Okay. Then the general solution, it's a homogeneous, right? So general solution would be c1 cosine of 3t plus c2 sine of 3t, right? Then we take the derivative of this because we want to apply the initial conditions. So it's going to be negative 3c1 sine 3t plus 3c2 cosine 3t. If x0 equals 3, that means what? Which one is 0? Sine is 0, so simply c1 is 3. And if x prime of 0 equals 4, that means 3c2 equals 4, so that c2 equals 4/3. And for c1, c2 given, already found, eventually we know x1 of t. The solution we're looking for is 3 cosine 3t plus 4/3 sine of 3t. That's the solution, right? That's how we learn solving these differential equations. That's a homogeneous one from chapter 5. Okay, now let's see how we can use Laplace transformation to solve this. So let me write down the equation again. The equation was x double prime plus 9x equals 0, and two initial conditions were given. x0 equal 3, x prime 0 was equal 4. What was the solution? X of t. Okay, so that was the unknown function we were able to find here. Now, think about it. If I knew the Laplace transformation of this function, let's suppose, so let x of s to be the Laplace transformation of x of t. Right? I purposely write it bigger in terms of s. So if I knew if x of s was known, what could we do? Well, we could go this direction, right? Take an inverse of it, and boom, we would find x of t. Right? So if we know the Laplace transform of x of t, called x of s here, then we would take Laplace inverse and we would find a solution, the unknown function we're looking for the differential equation. Okay, well, let's see how we can get this guy. Well, the only thing I have is this piece right here, right, with these two initial conditions. So if there was a way, if we could take Laplace of both sides of that equation, like x double prime plus 9x, of course the other side is 0, right? It's linear, so we get the Laplace of double prime plus 9, Laplace of x equals that side is 0. Well, we just supposed that this guy is simply x of s, the Laplace of function x of t. So 9 of s, the only unknown, the only piece that we don't know about is this guy. So how can we find the Laplace of a derivative of a function? Right? Because as soon as, let's say, for example, let's say we would get 1 s square or 1 plus s square x of s plus 9 x of s, okay? And then maybe, plus 3 equals 0. Then out of this equation, we can solve for x of s, right? So we solve for x of s. That's a function of s. We do inverse, and we get x of t. So what we don't know is that how do we find the Laplace of derivatives of a function? Okay, so let me erase that extra. Okay, let's erase that one as well. So that's the piece we don't know about. What's that Laplace? Okay. So for that reason, I'm gonna literally find the Laplace of a derivative, and then I can extend it to the second derivative and so on. So let me just go. Let's start with this. Okay, suppose Laplace of f of t we identified by f of s. Okay. Now, question is, what's Laplace of derivative of f? What's Laplace of f prime? In terms of f of s, right? What is this guy in terms of f of s? Well, we have nothing but the definition of Laplace. So the definition of Laplace was integration from 0 to infinity e to the negative st. Then the function we do in Laplace for taking Laplace, in this case, is derivative of f, and then dt. Okay? All right. Now, remember, I want to relate this. I want to make a connection between this and the original Laplace of f. Remember, original Laplace of f was, definition was 0 to infinity e to the negative st f of t dt. So I want to make a connection between this and this guy. There's only one technique of integration that we can do that. What technique is that? What technique of integration can make a connection? There you go, by parts. Right? So if you name this UDV, for example, UDV, meaning so we're letting dV to be f prime t dt, and let u be e to the negative st. Good. Okay. So what is this equal to? It's equal to uv minus integration v du. So we need v. What's antiderivative of f prime, guys? It's f of t, right? Yeah. And what's du? Taking derivative with respect to t, is going to be negative s e to the negative st dt. All right, let's substitute. So it's going to be uv. uv is e to the negative st f of t from 0 to infinity, okay? Minus, there's a negative here, so it makes it a plus. 0 to infinity s e to the negative st f of t dt. Okay? S is a constant here. Do you see it? So it can be pulled out. Remember, integration is with respect to t. So that can be pulled out. That means it's going to be s 0 to infinity. I'll repeat the other pieces. Okay, now I'm going to evaluate this guy. Remember, if you rewrite this, basically this is f of t e to the st, right? And normally we're talking about bounded functions like power functions or exponent trig functions which are bounded. Okay, so at infinity, when t approaches infinity, this is 0. Okay, tell me what happens if you plug 0 for t. Well, if you plug 0 for t, e to the 0 is 1, so we'll have f of 0. So that term is nothing but negative f of 0. Okay, now you guys tell me what that is. We have a name for that. In fact, it was the whole argument of we want to make a connection between this integral and that integral. I underlined them. There's a big name for it in the middle. F of s. There you go. So that's s times f of s. In fact, or Laplace of Laplace definition. Basically, that's the Laplace definition of this function. But we named it f of s right there. Okay, so the left side eventually is negative f of 0 plus s f of s. And what was this? This was the Laplace of f prime of t. Okay, so basically we wrote Laplace of f prime. I'm gonna ignore t. It's s. This is Laplace of f minus f evaluated at 0. Simple as that. Okay, and it's a formula. It works. For example, let's see. let's try for something that we already know. We already know come on. No, in fact, we know the other one, but we already know Laplace of sine of, for example, t equals what? Equals what was it? 1 over s squared plus 1, right? Okay, we already know Laplace of cosine t, but we just want to see if this formula works. Okay, what's the derivative of sine? So if this is f, then f prime is nothing but cosine of t, right? So according to this formula, Laplace of cosine of t, which is f prime, equals to s Laplace of f itself, which is sine t, minus f at 0. So f is sine, so sine evaluated at 0. So sine of 0 is 0. Okay, we already know what Laplace of sine is. It's 1 over s squared plus 1, and we have an s behind it, this guy right here, and there you go, we have s over s squared plus 1. And we already know what's Laplace of cosine, right? We just wanted to make sure this formula is something that works. Simple example of that. Okay, so by that setup, we can find the first derivative Laplace. Well, we can do this and find the second derivative, Laplace of second derivative. Here's how we're going to do it. So what's Laplace of second derivative? We don't have to do it by the definition.
Is that an
I can make
equals
a
or a
shortcut.
z right there?
That's an equal sign. Sorry.
Gotcha.
So we're talking about, I'm assuming this one. Okay, so Laplace of f double prime. Well, this is what I'm going to do. Simply let g be f prime. Okay, if g is f prime, what is g prime? It's f double prime. Okay, so Laplace of f double prime, I'm going to replace it with g prime. We already know the Laplace of first derivative. It's s Laplace of g minus g of 0. Is that correct? Basically, I'm applying this formula. I replace f with g. Now, let's plug g back. So it's going to be s Laplace, what was g? There was f prime minus, oops, we already know what g is, f prime of 0. Now I'm going to replace this with the formula of itself. So it's going to be S. So this guy is going to be S Laplace of f minus f of 0 minus f prime at 0. Distribute and and you get this. So Laplace of f double prime is s squared Laplace of f minus s f of 0 minus f prime of 0. And there's a nice pattern. In fact, if you apply this same thing to the third derivative, you'll see this pattern. It's going to be s cubed Laplace of f minus. Someone tell me what the next term is. You can open your mic, simply say it instead of typing.
Minus s squared Laplace f.
It's s squared times s squared is correct.
F of 0.
Nice. F of 0. What's the next one? S f prime of 0. And there's one last term. What is that one? F double prime at 0. So I can see the powers of S are dying. Eventually you get the order of derivative, which is one less than the original function's order of derivative, but all evaluated at 0, right? Let's write down the next one. So the Laplace of fourth derivative is going to be s to the fourth Laplace of f minus, s cubed f of 0 minus s squared f prime at 0 minus s. So decrease one power from s, add 1 to the order of derivative. Okay, so here's s squared, here's s. Here's first derivative, the next one is going to be second derivative at 0. And the last one, is the third derivative at 0. And that's it. That's where you stop, okay? So you can see that pattern. Let me write it down. Should I call it the theorem? Or, no. So the Laplace of nth derivative of f is going to be s to the n Laplace of f. So the only Laplace is showing up here. The Laplace of the original function is only right there. The rest is going to be, polynomials of s. Like this whole thing is just a polynomial of s. Okay, these are constants. These will be given. F prime is 3, f double prime is 0 is 5, and so on. So then it's going to be decrease 1 from the power, so it's going to be s to the minus 1, and the first one is f of 0, minus s to the n minus 2, f prime at 0, minus, s to the n minus 3, and then f double prime at 0, minus, do this until minus you get. Let's write down the one last one. It's going to be s, and then f minus 2 derivative at 0, and the last one is basically the n minus 1th derivative at f at 0. Okay? I mean, the other way you can sort of memorize it is that the sum of the power of s and the order of derivative of f is always n minus 1. What's the order of derivative on this term is 1. What's the power of s? N minus 2. N minus 2 plus 1 is n minus 1. So that's another way sort of memorize it. Same as this one, the power of s is 1. The order of derivative is n minus 2. You add them, you get n minus 1. Okay? All right. Now, since we know this, let's see if we can find the solution of the differential equation we already found using, characteristic equation by doing Laplace. So let me write it again. So apply or using Laplace to find solution of, okay, so differential equation was x double prime plus 9x equals 0, right? And x of 0 was a 3, and x prime at 0 was equal 4. Okay. So remember, we are the assuming Laplace of x of t is x of s. Okay, meaning Laplace inverse of x of s is simply x of t. That's the connection between the two. Okay, so let's go ahead and take Laplace both sides of this guy. So we already know it's going to be Laplace of x double prime plus 9 times Laplace of x equals 0. We already know this one is 9 times, Laplace x of s, right? So let me replace that with x of s, 9 plus. I need to leave some room. So this one, 9 x of s equals 0. Okay, now I'll write down the Laplace for x double prime. Well, we know what the setup is, right? So it's going to be s Laplace of x minus s, x at 0 minus x prime at 0. Right? Basically, this is what I used. That's the line I used. I replaced simply f with x. So Laplace of x double prime, s square Laplace of x minus s, x at 0 minus x prime at 0. Good. All right. So we have s squared. We have a name for that. That's x of s, the transformation of x of s, minus. We have a value for that. What is x of 0? It's given right there, right? 3. So that's 3s minus 4 plus 9 times x of s equals 0. Now, this is not a differential equation anymore. Do you see any derivative sign in there? The answer is no. That's the nice thing about transforming the differential equation into an equation of Laplace transforms. So initial equation was a differential equation. We had derivatives of the functions showing up. When you transform this, it's simply an algebraic equation. There is no derivative in it. And you want to solve for x of s, right? So bring all the variables to one side and the known parts on the other side. Pull out the coefficient or the common part by the coefficient of x of s, right? So I want to solve for x of s. I have two terms having x of s. So I can bring these to the other side. So it's going to be s squared times x of s plus 9 x of s equals 3s plus 4. Agree? Okay. Now I can factor x of s. So it's going to be s squared plus 9 equals 3s plus 4. Right? And I want to solve for x of s. What do? Well, you want to undo that. So divide both sides. So x of s is going to be 3s plus 4 divided by s squared plus 9. Good. So we found this. Now, what do I want? I want that function in terms of t. Remember, this is the space of Laplaces. This is in a different space, right? So I want to go back to this space where my function, original function, is in terms of t. So what was that? That was the inverse of that x of s. So the unknown function x of t that I'm looking for is the Laplace inverse of 3s plus 4 over s squared plus 9. And by the way, can someone remember what the solution was that we found on the first page? Let me go back up. The solution where we find C2 and C1 and C2. Damn, you went. No, it's not here. Went too
X of
far.
t was 3 cosine 3t plus 4/3 sine 3t.
It's right there. Okay. Yeah, thanks.
Oh.
So let me write it down. So we already know the solution was 3 cosine, was it 3t or 2t? 3t plus 4/3 sine of 3t. Okay. We found the solution by setting up the characteristic equation. Now we're doing it Laplace. Okay. So let's continue here. How did we find this Laplace inverse? Well, we split it up to two terms. So 3s over s squared plus 9, right? Plus Laplace inverse of 4 over s squared plus 9. Constants can be pulled out, so it's going to be 3 Laplace inverse of s over s squared plus 9 plus 4 can be pulled out, Laplace inverse of. All right. Since you're going to apply Laplace inverse, and there should be a constant, that matches with the square root of that. So you're going to need a 3 in there. That's why you divide by multiply by 3. And now there you go. You're ready for doing the inverse, right? What's inverse of this guy? That's exactly cosine 3t. With that 3 as the coefficient. 4/3 inverse of that is Laplace. It's 3 sine 3t. That's one simple application of Laplace transform and the inverse of Laplace. Could you scroll back up a little bit, please? How far? Olsen? Is it for good enough? Okay. Any questions? Let me see. The rest is a bunch of problems and then application. You know what? Let's do something interesting. Is there? You're gonna like this one. Solve the linear system x prime equals to let's do number 11. So number 11 is 2x plus y prime equals to 6x plus 3y. X of 0 is given 1, x prime of y of 0. Y of 0 is given as negative 2. Okay. That's a linear system, right? What method did we use to solve this equation and find solutions? X of t, remember, we're looking for x of t and y of t satisfying the system. How did we do it? We found, what was the first thing you find? Eigenvalues, eigenvectors. Then you find those two functions, right? If you want a two fundamental matrix, you can do that, right? And all that stuff. Now, here's the beauty of Laplace. You have none of that crap. This is how you do it. Simply using Laplace, simply assume the Laplace of little x is x of s, and the Laplace of little y, when I say x, I mean this function, and by y, I mean that function right there. It's y of s, okay? Of course, if I have them, I take inverse, and that's the solution. Okay. Take Laplace of this system, of both lines. So we're going to get Laplace of x prime equals Laplace of 2x plus y. The other line, we have Laplace of y prime equals Laplace of 6s plus 6x plus 3y. Okay. The left side, it's simply 2x of s plus y of s, correct? And then the other one, you have 6x of s plus 3y of s. Those are the right sides of each equation. What's the left side? We know the Laplace of a derivative, right? It was x of s minus x at 0. And the other one is s y of s minus y at 0. Y of 0, x of 0 are given. So let me rewrite them again. So it's going to be s x of s. That's multiplication. Minus x of 0 is 1 equals 2 x of s plus y of s. And the other one is s y of s minus y of 0 is minus 2, so makes it plus 2 equals 6x of s plus 3 y of s. Now, you have two equations. How many unknowns do we have? Remember, s is known. Like numbers are known. The only unknowns are x of s and y of s. We have two equations, two unknowns. We should be able to solve for them. Use any method. It's algebraic. This is algebra. It's nothing. This is not differential equations, not even calc 1. It's not even algebra 2. It's algebra 1. It's pre-algebra. Okay? So whatever you need to do and solve for x of s and y of s. Let's do it for this one. First of all, you can simply solve for one of them in terms of the other one in one equation, plug it back, and then find the other one. So for example, out of the first one, let's go ahead and solve for y of s, okay? So from the first one, s x of s minus 2x of s minus 1 equals y of s. That's it. Now go ahead and plug it for in the other one. Let's first of all simplify the left side. So here, y of s is going to be what? S minus 2 times x of s, then minus 1. Okay, these are two different terms. Now from the second one, we have s, y of s. So y of s is that guy right there. It's s minus 2, x of s minus 1, plus 2 equals 6 x of s plus 3 times y of s again, which is s minus 2, x of s minus 1. I mean, we could have combined the 2y of s here. It's okay. Let's distribute. So we get s times s minus 2 x of s minus s plus 2 equals 6x of s plus 3 times s minus 2 x of s minus 3. Right? Let me check my algebra. If I'm making a mistake, guys, I know you're saying 2. What's going on? What do you mean by that 2? Am I making a mistake? Do you have an error? Will. That was a number. Oh, that was a number of unknowns. Thank you. I thought you mean missing or I have an extra 2. Okay, thanks. Okay, so let's combine these three terms, factor x of s, and then solve for it. So let me bring these two terms out of side. So I get x of s. Let's factor. So we get s squared minus 2s, right? If I bring 6 to the other side, it becomes negative 6, and that becomes negative 3s plus 6. Agree? And what goes the other side? The other side becomes s minus 2 minus 3, which becomes 5, negative 5. Right? So again, I have these three terms. They all have x of s. I'm bringing them to the left side. I factor x of s. That's what's left after you factor x of s. right? At the same time, it distributes, so it's going to be s squared minus 2s. Negative 6 is coming from here. And then these two together, they make those two terms with the opposite signs, okay? So it's going to be x of s equals, let's simplify here. It's going to be s, these two cancel, so we get s squared minus 5s, okay? So that's, s times s minus 5. Oh, multiplication, what am I doing? So that's multiplying. Let's erase it. So times s minus 5, and the right side is also s minus 5. So this is very nice. S minus 5 cancels, so x of s is 1 over s. Okay. Now that we have x of s, I can plug it here and find y of s. So, and y of s equals s minus 2 times 1 over s minus 1. Let's do that algebra. So it's going to be s minus 2 over s minus s over s, and that becomes what? Negative 2 over s. Negative 2 over s. Right? Okay. And, well, let me erase this. So this is what we have. Your x of s is 1 over s, and y of s is equal to negative 2 over s. Now, to find x of t, you simply take Laplace inverse of 1 over s. You tell me what that one is, and y of t is Laplace inverse of negative 2 over s. Or you tell me what the first one is. Yep, it's 1, and the other one is negative 2. So the two functions satisfying these two equations and satisfying those initial conditions is basically constant functions 1 and negative 2. Okay, but that was a very simple example, and you ended up with simple expression for x of s and even y of s, and we could easily take Laplace inverse. But so that's another another good application of a Laplace transformation. Then not only you can solve differential equations, one variable differential equations, you can also solve systems of equations. Okay, any questions so far? Damn, that became 14 pages of notes. I mean, of course, this is bigger than normal, and but so questions. We can do one more example. We have another 5 minutes, 6 minutes. Oh, you know what? Let me do Laplace inverse of. In fact, it's very simple. Laplace inverse of a huge function, then you have to do partial fractions. Because, in fact, for all of the cases solving differential equations, you eventually, you find an x of s, which is a crazy function of s, and then you have to Laplace inverse this, right? The only case you can do this if, you can break this down to simple functions of s, and, maybe one of them is e to the t, the other one is sine of 3t, and one is, cosine h of 2t, something like that. But before that, you should be able to break this function, the huge function of s, down to small pieces. And that's done by simply doing partial fractions. We'll do an example right away. Okay. Let's do questions. Book questions are simple, guys. Let's do... Should I start with a simple one or a complicated one? Huh? Simple? Simple. Okay. Let's do number 19. So we want to find the Laplace inverse of 1 over s times s squared plus 9. All right. Doesn't really know the inverse of that. Like, what function of t generates that Laplace? I would be surprised if you know. You can still, throw out something. It's okay, even if it's wrong. Maybe you probably are able to make a connection between the s squared plus 9 in denominator and probably one of the trig functions. I'm assuming you may want to do that, attempt doing that, right? But there's that s in there. So yeah, we want to split it up. So we want to basically split this up to, maybe s, two fractions with one denominator s, and the other one is s squared plus 9, right? And we did do this. We did it in Calc 2, right? And the technique was called partial fraction. Okay. Now, question: what kind of numerators are we expecting for the first fraction? Like on top of s, what kind of expression are you expecting in terms of a polynomial? Constant. Beautiful. Now, what kind of, constant, a, b, it doesn't matter what way you want to call it. What kind of expression are you expecting in the second one, s squared plus 9? And then remind you, this is it's linear. Remember, s squared plus 9 is not factorable, okay? So for that reason, we want a polynomial of 1 degree less, which is linear. So in this case, let's go with bs plus c, okay? And we add the two fractions, it has to be equal to the initial one, and then set it equal to each other. So 1 over s times s squared plus 9 has to be a over s plus bs plus c over s squared plus 9. Okay, so you multiply both sides by the common denominator, which is s. So multiply both sides by s times s squared plus 9. And if you do that, on the left side you get 1, and on this side you get a times s squared plus 9, and plus on this side you get s times b times s plus c. So you get a s squared plus 9a plus b s squared plus cs. Okay, let's put them together. So on the left side you still have 1. A plus b s squared plus cs plus 9a. So on the right side you have a second degree polynomial of s, right? Coefficient of s squared, coefficient of s, and the constant term. And it has to match with the coefficients on the left side. What are the coefficients of left side? Well, it's 0s squared plus 0s plus constant. Now put them together. So a plus b has to be 0. C has to be 0. And 9a has to be 1. So for that reason, a is 1/9. Of course, c is 0 already. And b is negative a, which is negative 1/9. Okay, now let's go back up. So the Laplace inverse, initially we had what? 1 over s times s squared plus 9 equals to Laplace inverse. Okay, so the first one was a, so it's negative 1 over 9 s plus c ended up being 0, so we have bs. So bs is negative 1/9 s over s squared plus 9. Now we're ready. So it's going to be negative 1/9 Laplace inverse of 1 over s plus minus 1/9 Laplace inverse of s over s squared plus 9. Okay. What's that one? What function is that? You can go back to your table.
It's 1.
There you go. It's 1. So it's negative 1/9 minus negative 1/9. And what's that guy? There's s on top. So it has something to do with cosine. And the denominator is s squared plus. So
Is it
it's
cosine 3t?
Yep. So the Laplace inverse of that expression in terms of s is negative 1/9. Oops, I have two negatives, so let me erase one of them. There you go. Negative 1/9 Someone can put it this way, so you can factor the negative 1/9, so it becomes 1 plus cosine 3t. Okay. Question on that?
Can you go back to the partial fraction part a little up?
Yeah.
Why does a plus b equals 0?
Because a plus b on the right side is the coefficient of s squared, and there's no s squared term on the left side, or coefficient of s squared is 0. So that's why the coefficients basically have to match. Like this coefficient have to match that one, this coefficient has to match this one, and the constant has to match that number. It's like you're setting two polynomials equal to each other, so the coefficients have to be the same.
Wouldn't the first term be positive 1/9? Like where A is supposed to be on the final answer?
You are right. So we have an extra negative in there. You're right. So let me erase that. Thank you. So erase that. Where else do we have it? Erase that. Erase that. So for that reason, let's make that positive. That means this term is going to be negative. Okay. I think it's correct now, isn't it? Hopefully. Oh, Jack Foster, same thing. Yeah. So it was plus 1/9. Okay. Any other questions, guys? So I'm gonna update the homework on 10.1, and I add homework problems for 10.2, and you guys can work on it. And a couple things on 10.2. We didn't talk about Laplace of t f of t. We can talk about that. And also, we did talk about Laplace of f prime. Someone might ask, well, is there a formula for Laplace of integral? The answer is yes. So we can come up with the formula for Laplace of those as well. Sometimes they're useful. And yeah.
Can you go over putting 1/9 back into the inverse Laplace? It's a little up. Right there.
Where exactly?
Laplace inverse equals Laplace inverse right there in the middle.
This one right here?
Yeah, can you explain why the 1/9 on the right side is negative s, negative 1/9 s?
Because our initial setup is coming from this guy right here. You see it? So it's a over s plus bs plus bs plus c over s squared plus 9. So we ended up at c equals 0, so that's 0. I don't want to write that down. So that ended up being 0, and then b was negative 1/9, right?
Because a plus b equals 0.
Yeah. So if a is 1/9, that means b has to be the opposite sign. So that's why it's negative 1/9.
I gotcha. Thank you.
Yeah. Okay. I'll update the homework, and actually 10.3 is in the like using partial fractions to find Laplace inverses. So we'll continue with that on Wednesday. So for that reason, on Wednesday this time, I teach first, like first hour, and then I answer some questions, and then you guys can take the quiz for 30 minutes at the end, plus 10 minutes submitting them. Okay? Hold on a second. We have the quiz at the beginning, at the end, because 10.3 is again partial fractions. So that will be helpful to you guys seeing more problems using partial fractions to find inverses. Anything else? Okay, take care. Stay at home. Be safe.